So, the form that I would like to highlight now next is the solution of the Hamilton-Jacobi-Bellman equations, right. Okay. So, Jacobi-Bellman equations. So, this is an alternate form. Students who have attended my previous lectures will realize that these equations are similar to the Hamilton-Jacobi equation, which used to find the generating function, and through the generating function we used to find the optimal or the extremal curves via taking certain derivatives, right. So, this time we will see that our generating function in our Hamilton-Jacobi-Bellman equation is the functional itself, right. So, well, there is, so this is Bellman equation. Okay. Okay. So, what have we got? So, before we start, let me just state the principle of Hamilton-Jacobi-Bellman optimality condition. So, it says that the optimality condition by Hamilton-Jacobi-Bellman says that any portion of the optimal curve is optimal, right. So, or in other words, it does not depend what the solution was at previous times, but the times that follow which satisfies this HJB or Hamilton-Jacobi-Bellman equation will always be optimal in the future time, right. So, this is an alternate method for solving optimal control problems, So, let me start with the Bellman's principle of optimality. The Bellman's principle of optimality. Okay. So, as I said, the principle says that any portion of the optimal curve is optimal. So, any portion of the optimal trajectory is optimal, right. Okay. So, as I said, the meaning of this statement is it does not depend on the previous times whatever the solution was, we just need to look at the future times, and the solution to this equation will guarantee optimality for the solution at the future time, right. Or so what I just said is the following. So, or the optimal control, the OC, the optimal control has the property that regardless of previous decisions or controls, regardless of previous decisions or controls, the remaining decision is an optimal policy, right. The remaining decision is an optimal policy, right. Okay. So, let us start our basic setup of the problem. So, we start by defining our performance index. So, defining our minimum. So, we start with the optimal or the minimal performance index evaluated at the start condition. So, we define the minimal performance index to be J star of x star comma t, which is the integral from T0 to Tf of V of x star u star tau d tau, right. Okay. Let me denote this equation by 1, and our interest now is to find the initial value of this functional at time point t0, right. So, what is the starting point of this starting value of this functional which leads to this optimal solution, right. So, that is what we want. So, our interest is to find j of x of t 0 comma t 0 for any unspecified initial condition, right. So, let me before I start describing the problem, note that I can always describe my total time derivative of j star at x star comma t. Well, I am writing a shorthand here. So, the total derivative by chain rule will be partial j partial x j star at x star comma t. So, this is evaluated at the start condition, and well, so we have x star being an unknown. So, we keep it as it is times partial x star partial t, which is x star dot, right. So, let me use a bracket plus partial j partial t at the start condition, okay, x star comma t. Okay. So, we have used nothing but the chain rule here. Okay. So, then from here we use my plant condition that x bar dot is f. So, this is nothing but del j del x bar at start condition times f at x bar star u star t plus del j del t at the start condition. So, that is what the total derivative of j star at t is. Okay. And then notice that we can always evaluate this total derivative. Let us look at our expression for j. So, notice that so t is the variable. So, let me denote t 0 as my t, right. So, my t is the variable. So, t appears as the lower limit. So, from here from 1, if I differentiate j or take a ordinary derivative of j with respect to t, I get the answer to be minus of v at t, right. So, from 1 I see that the ordinary derivative of j star at t gives me minus v of x star comma well, what is the argument, x star u star comma t, right. Okay. So, let me call this as 2 and let me call this as 3. So, I can use 2 and 3 to arrive at an equation. So, from 2 and from 3 I see the following equation partial j star partial t, right. These are all evaluated at start condition here, plus partial j star at x star times f evaluated at all the start condition. So, this is an equation which is being solved at the optimal value, right, plus v of x star comma u star comma t is equal to 0, right. Okay. So, now this equation is nothing but our HJB or Hamilton Jacobi Bellman equation that we were after. Okay. So, now further let us simplify this equation by introducing the Hamiltonian function. So, introduce our Hamiltonian H function to be v of, so this is at start condition x star u star comma t plus partial j star partial x star partial j star partial x star of f comma u star comma t. and so this is our start condition, and let me call this as 4, and once we introduce this 4 into this boxed relation, I see that my equation changes to. So, using 4 I have that partial j star partial t plus h at x star comma j star j partial j star partial x star comma u bar star comma t is equal to 0 for all t in t 0 to t f, and so this is t 0 to t f. Well, I need to be careful here, it is a half open interval, and that is the form of the HJB equation that we are after. So, this is my equation number 5, and this is the form of HJB equation that we will be using in our examples. Okay. Well, there is also the set of boundary. So, we have boundary conditions, we have not introduced our cost function in our functional. So, that cost function appears in the form of a boundary condition. So that does not vanishes. So, with boundary conditions as follows, I see that j star at x star t f comma t f is equal to 0 and j star at x star t f. Well, so this is the case when s is identically 0, the cost function, and otherwise this is also equal to the value of the cost function at t f. Okay. So, I call this boundary condition as my 5a. Okay. So, we still retain the form of the performance index without the cost function, because the cost function appears in the form of a boundary condition. Okay. So, then we can compare this HJB equation with our regular Hamiltonian formulation or the Pontryagin Hamiltonian function. So, comparing our HJB equation or HJB Hamiltonian. So, this is the Hamiltonian that we have noticed, that this is the Hamiltonian that we have assumed. Notice that this Hamiltonian has all the components similar to the Pontryagin Hamiltonian, except this circled quantity, which initially in the Pontryagin function was lambda, right. So, that is the difference. So, we compare the HJB Hamiltonian with the Pontryagin Hamiltonian. The Pontryagin Hamiltonian, and I see that in that case lambda star must be equal to j del x star, right. So, both the theories they converge if I have lambda, the Lagrange multiplier, replaced by the partial j partial x at start condition. So, let me call this condition as alpha 1, and my in that case my optimal co-state equation which was lambda. So, lambda bar dot is minus del h del x, which is the same as my Pontryagin setup. So, this is alpha 2, right. Or if we are to compare my alpha 1 and alpha 2, we see that we have a relation between j and h, right. So, comparing, so this is from our Pontryagin theory. Okay. So, comparing our results in alpha 1 and alpha 2, I see that the time derivative of partial j partial x, the time derivative of this quantity is minus of partial h partial x, right. So, this is also equal to d dt of lambda star, and this is also equal to minus partial x of h x x star comma partial j partial x star comma u star, right, comma t. Okay. And so that is the relation between j and between h, right. So let us now summarize our solution methodology, and then we will look at an example, right. So the solution methodology for our HJB setup is as follows. So solution summary. Okay. So what do we do? First we form, so the step 1 is form the H function, form the Pontryagin H function, which is h of x bar u comma j star x t, right. So our j star, so instead of our lambda, so j star x plays the role of lambda or the Lagrange multiplier. So I must say that this is our HJB, right. So yeah, so this is our HJB Hamiltonian, form the HJB Hamiltonian, sorry, we are discussing the HJB setup. So form the HJB Hamiltonian, which is also equal to V of x bar u bar t plus j x star of f of x bar u bar comma t, and then we are going to minimize as we have done in our Pontryagin case. Right now we are looking at an unconstrained case. So we minimize h with respect to u bar by setting partial h partial u at start condition is equal to 0. So that is for our unconstrained case, and then we find the optimal Hamiltonian. So say from here I see that u bar star is equal to h of x star comma, we have all the other variables t, right. We also have a variable j star x. So j x star comma t, right. So now in the step 3 we are going to rewrite our Hamiltonian. So find optimal Hamiltonian now by substituting our control, optimal control is found in step 2. So find the optimal Hamiltonian, h star of x bar star h of x bar star comma j x star comma t and comma j x star comma t, right. We find the optimal Hamiltonian, and from there once we have the optimal Hamiltonian we plug it into our HJB equation to find j x star, the optimal derivative of the functional. So step 4 is solve the HJB equation, which is j t star plus h of x bar star comma j x star comma t set equal to 0, and with my boundary condition j star of x star at T f comma T f which is also equal to s of x bar of T f comma T f. Okay. So my HJB equation is the following with the boundary condition as shown. and then I am going to use, once we find the solution j, we have to take the necessary derivatives with respect to x and t to find our optimal control, right. So, step 5 is use j star in step 4, use j star in step 4 to evaluate, use j star in step 4 to evaluate j x star and substitute into u star, in step 2. So, use j star in step 4 and evaluate our partial derivatives j x star and substitute in our equation number 2, which will give me my optimal control, right, to give me my optimal control solution. Okay. So, that will complete the description of the problem. Okay. So, let us look at a quick example of this solution methodology. So, the problem says the following. So, this is our example number 2. So, the problem is given a first order system x dot is minus 2x plus u, typically all functions of t, and my performance index j, which is equal to half x square at T f plus half integral from 0 to T f x square plus u square dt. Find the optimal control, right. So, we need to find the optimal control for this setup. It is a one variable problem. So, the step 1 we use the stepwise solution methodology. So, step 1, well, before even step 1 we have to identify the various components here. So, my v, the quantity inside the integrand is half x square plus u square, right, and my cost function s is half x square, right. So, let us start with the solution methodology. So, step 1, h, we have to first write the Hamiltonian h of x star comma j x comma u star comma t. Well, did we begin with u star or did we begin with u? We began with u, right, because we want to find we start with the general Hamiltonian. So, my values are as follows. So, h at these values are v plus j x times f, right. So, we are going to plug all these relations. So, v is u square plus x square by 2 plus j x of f, f is minus 2 x plus u, right, and then in step 2 I take the partial derivative of h with respect to u. I see that u star becomes minus j x, right. We just take the derivative and we will get our answer. So, u star is j x, and step 3 is well, using the solution found in step 2, I just replace my optimal value of u star in our Hamiltonian. So, my optimal Hamiltonian h of x star comma u star, well, it is no longer a vector. So, x star comma u star, well, so comma j x comma t, j x star as well, is equal to, so instead of u star I have j x square, right. So, that will be, after simplification I get the following quantity. So, minus half j x square plus x square by 2 minus 2 x j x, right. Okay. So, what have we got here? So, we see that now the next step. So, we have found the optimal Hamiltonian, the next step will be, so this is all evaluated at the start condition. The next step is to write down our HJB equation. So, my HJB equation will be, so my HJB equation will be JT plus H is equal to 0, or this means that JT minus half Jx square plus x square by 2 minus 2x Jx is equal to 0. So, note that now we are to solve for the unknown j in this problem, and to do that, well, let us recall the way we used to solve Hamilton Jacobi. In our previous discussion, we have shown that one method of solving Hamilton Jacobi equation, namely the separation of variable. We are going to use that idea and separate time and space this time. Okay. Well, assuming that these can be separated, right. So, that is a major assumption, may not hold all the time. Okay. So, what have we got? We see the following. So, assume, so step 4 is we are going to solve. So, have we already used step 4? Yes, we have used. So, solving, so solve HJB equation, and let us see what it does. We are going to assume that my j has the following form. Notice that I have, so I have just used just a hit and trial by separating out my function of t and the function of x. Now, well, it is not exactly hit and trial, but it also a bit of observation. Notice that why have I used x square, because notice that in my original HJB equation I am getting a term x square, right. So, that gives me an indication that if a function h needs x, function of x needs to be separated, it must appear as a quadratic function, right. And then all these halves also suggest that we will have a constant sitting outside. We will see that this form nicely separates out this HJB equation. Okay. So, also, but before that, let us also see what is the boundary condition. The boundary condition was j, the boundary condition was the following: j at x at Tf comma Tf, j at x of Tf comma Tf is equal to s of x of Tf comma Tf, right, and my cost function is half x square Tf. Okay. So, my cost function is the following. Now, if we plug our form our Jx into this relation, I see that I get a boundary condition p at Tf is equal to 1, right. So, at time point t equal to Tf, the separable form must satisfy p at Tf is equal to 1. Okay. So, we are ready to solve. Notice that this form of Jx will give me the partial j partial x to be p times x, right, and my Jt to be half p dot, the dot means the derivative of any function with respect to time t times x square, right. And when we plug it into we plug it into my HJB equation, I see that I get the following equation: half p dot of t minus half p square of t minus 2 p of t, right, plus half. This is also equal to 0, right. and times this is the common what we had was, once we plug our form of j, we will get this this factor times x square, right, and then of course, this is set equal to 0. This is all evaluated at the start condition. Now, we cannot have x equal to 0 as the solution, because we will then get a trivial solution. So, then from here the only non-trivial solution will be given by the following ODE: p dot by 2 minus p square by 2 minus 2 p plus half is equal to 0, and this is a standard first order linear constant, not linear, but constant coefficient ODE. And let me write down the solution to this problem. Students are expected to have a background in standard or solution methods of first order ODEs. I see that the solution is given by the following function: square root 5 minus 2 plus square root 5 plus 2 times 3 minus square root 5 divided by 3 plus square root 5 times e to the power 2 square root 5 t minus t f divided by 1 minus 3 minus square root 5 by 3 plus square root 5 times e to the power 2 square root 5 t minus t f. So, what have I found is that this function p is going to certainly satisfy the boundary condition. So, this first order ODE will satisfy this boundary condition, and students are requested to check that this is indeed the solution. And finally, my final step is to get the optimal control. So, step 5, my optimal control u star is given by minus j x to begin with. This is now at the start condition, which will be minus p of t times x, where p is given by the following expressions above, right. So, note that as we see that as t goes to infinity, my function p goes to a constant value, which is square root 5 minus 2, or my optimal control will be of course purely a function of x, right. So, that is just an observation, and that is how we solve this class of problems. So, solve the Hamilton-Jacobi-Bellman equation and find the optimal control by taking the partial derivative of the solution with respect to x. That will give me my optimal value of the control function. Okay. So, now let me finally introduce two more methods of constraint optimization. So, what happens if we now solve constraint problems where the constraint itself are inequalities, as we had seen earlier. So, how to set up the Hamilton-Jacobi-Bellman equation? We will see that we are going to introduce, similar to our discussion in our earlier lectures, we are going to introduce an extra variable and hence a non-holonomic constraint, which will absorb the inequality constraints. Okay. So, let us see what I just said. So, let me just wrap this up.